So we are very pleased to have Dr. Joy Tropp from Caltech University to give us a special one-word seminar and a special MSc colloquium today. Joy Tropp is still family professor of applied and computational mathematics at the Caltech. His research centers on applied mathematics, machine learning, data science, numerical algorithms, and random matrix theory. Some of his best-known contributions include matching pursuit algorithms, randomized SVD algorithms, and the matrix concentrated inequality. Professor Tropp obtained his PhD degree in computational applied math at the UT Austin in 2004, and he joined Caltech in 2007. He has a lot of awards. For example, he won the Presidential Early Career Award for Scientists and Engineers in 2008, and he was recognized as a highly cited research in computer science each year from 2014 to 18. He is co-founder and the section editor of the SIAM Journal on Math of Data Science, and he was co-chair of the Ingrail 2020 SIAM conference on the Math of Data Science. Professor Tropp was selected as SIAM Fellow in 2019 and IEEE Fellow in 2020. And today he will talk about locate proposed Cholesky addressing the challenge of large-scale kernel computations.
Thank you, Long Sue. It's a pleasure to be here. I'm sorry that this visit is out of term and that I don't have a little bit more time to stay and talk with y'all, but this is my first time in Michigan State, and as I said, I'm happy to be here, and the campus is very beautiful, so especially in May.
Always like this in the winter too.
I taught at the other University of Michigan for 3 years, so I'm well aware of what it's like in the winter.
We have a dome we put over campus.
Awesome. Shall we get started? Okay, so what I'm going to be telling you about is something that's a little bit specific, but there's a broader theme that I'd like to begin with. So over the last 20 years or so, there's been a change in the way that people think about linear algebra computations, where in the past, these algorithms were almost always deterministic. And recently, people have realized that using probability inside these algorithms can make them more efficient and more effective in practice. And so what I'd like to tell you about is one of the simplest randomized algorithms for a linear algebra problem that comes up in particular in kernel computations, although it has an even simpler linear algebraic interpretation. And in spite of the simplicity and I think naturalness of this algorithm, nevertheless, it seems that no one has actually written it down before. So I'd like to tell you about this. And again, the broader theme is that randomness can help us perform computations that in the past might have been challenging or unreliable. Okay. So this is joint work with a few students and postdocs at Caltech. So the main driver of this project was Rob Weber, who is a student of John Weir at NYU, who's going to be on the job market next year. And other contributors are Yifan Chen, who is finishing his doctorate and going for a postdoc at NYU.
Hi.
And
Hi, Joey. We cannot see your slides.
Oh, you can't see the slides. Do I need to there again? Pause. Okay.
Okay, now it works.
Oh, I guess you need to stop the share, switch to full screen first, then share.
Non-community.
Screen sharing is fair to start. Try again later. Let's try that one. question is how we get to Zoom. It doesn't want to do both of these things at the same time.
Yeah.
Is that moving?
No.
Yeah, the top two by resume once you go.
Sorry, do what?
Resume.
Go to full screen and then resume. How do I do that?
So the green triangle up in the top. Green triangle.
Ah, resume share. Or not? Not ideal, but we will get by. We shall overcome. All right. And the other contributors might grab me early. All right. Good. All technical problems are resolved. Great. Okay. So let's start with some background. So the linear algebra problem we're going to be talking about today is a low rank matrix approximation. So you have some big matrix and you'd like to approximate it by a low rank matrix for one of several reasons. You might like to identify structure that's latent in the matrix by, for example, finding the leading singular values and singular vectors. You might also like to use this approximation of the matrix as a tool to accelerate downstream computations. And in particular, these low rank approximations, if you apply them to kernel matrices that apply within kernel methods, I'll tell you a bit more about that later, you can use the approximation in place of the full kernel matrix to speed up inference tasks like prediction, interpolation of data, and clustering. Now, the problem with kernel matrices, again, I'll explain more about this later if you're not familiar with the subject, is that they involve an n by n matrix where n is the number of data points. And as you know, these days, n might well be hundreds of thousands or millions or billions or trillions. And so when you square that number, you wind up in a world of pain. So on a laptop, you can handle about 10, maybe 100,000 to 1 million data points, maybe. And if you use a workstation with specialized software engineering, you might be able to get to 1 billion data points. But that's only if you make a lot of approximations. And so the goal of this project was to understand whether we can perform kernel computations for huge data sets, say 1 billion or more points, on a laptop computer. And the hope then would be that if you had industrial or governmental resources that you could scale it even farther. And one of the reasons we've seen so many advances in machine learning in recent years is the scale of the data that's going into training these procedures. And it's the same thing here with kernel methods. The more data you have, the better the models that you can build. Okay, so our goal is to provide a fast, robust approximation method for kernel matrices. And this in particular has some computational implications because with a kernel matrix, you pay every time you look at an entry. And so it's a bit different from the some of the models that come up in other numerical applications where, for example, you're allowed to multiply the matrix by vectors. And the main result, which I will try and support, is that the randomly computed Cholesky algorithm, which I'll describe to you, is the most efficient method in practice for approximating a PSD matrix, such as a kernel matrix, when you have to pay to look at every entry, every time you look at an entry of the matrix. Okay, so this is all high level. Let me go into the details about what a kernel matrix is and why it might be interesting. So the kernel is a general method of similarity between is a function that provides a general way of describing the similarity between a pair of data points. So if xi and xj are two data, you plug them into the kernel and the kernel says these are alike or they are unalike. The bigger the value of the kernel, the more alike they are, the smaller the value, the less alike. we will assume that K is a positive definite function, which means that when you tabulate the similarities among any set of data points in an n by n matrix, that yields a positive semi-definite matrix. Okay. And so one very familiar example is the Gaussian kernel, which simply takes the squared Euclidean distance between the data points and runs it through the exponential. Okay, so when points are very close, the similarity is 1, and when they're very far away on a scale of the bandwidth sigma, so 3 sigma, 4 sigma, the similarity is very small. So this localizes points in Euclidean space. Points that are close together are similar, points that are far away are dissimilar. And as it happens, this is indeed a positive definite kernel function. So for any set of n data points in our D, the kernel matrix you get by tabulating the similarities is always positive semi-definite. So here's a specific example. So imagine you've got 3 red data points and 3 blue data points, which are drawn from 2 different clusters. So this is just intended to be illustrative. So if you choose the bandwidth to be similar to the radius of the cluster, these red points are likely to be similar with each other, and these blue points are likely to be similar with each other, and the red points and blue points are likely to be dissimilar. You can see that in the values, which are tabulated inside this kernel matrix, where the red points have these similarities, the blue points have these similarities, and the off-diagonal blocks have smaller entries reflecting the dissimilarity between the points in the different clusters. Okay. So by using this kind of radial basis function as a measure of similarity, it helps you localize points in spatial clusters. Okay. Any questions about the definition of the kernel matrix or how it helps identify the similarity of these clustered points? Okay, great. So what are kernel matrices for? So kernels are a very flexible way of describing similarity among data points. In fact, the data doesn't even need to be in a Euclidean space. And once you have this kernel matrix, you can do all sorts of things with it. You can solve a least squares problem with this kernel, or a regularized least squares problem to do prediction of a function defined on the data points, if you have some of the values available. You can interpolate the data points with by solving a linear system, and you can also do clustering, as I've shown you on the previous slide. And to do that, you need to compute the eigenvectors of the kernel matrix. And you can see in this example that the eigenvectors, the leading eigenvector tends to be positive here and negative here, roughly, which will identify points in one cluster versus another cluster. And if you take more eigenvectors, you can also use them as a means for defining clusters. I'll talk more about that later. Okay. Now, the problem with all of this is that when you have n data points, the kernel matrix is n by n, and it's very expensive just to compute the entries of the kernel matrix, let alone perform linear algebra with it, because most linear algebra operations are cubic in it. Okay, so that makes you sad. And what's even worse is that moving the data around from disk to RAM to cache is also a leading cost, because communication is actually a lot more expensive than arithmetic. So we're trying to find ways of taking these large data sets and working with the kernel matrix implicitly so that we don't have to pay for the full cost of the forming the matrix, moving it around, or doing linear algebra with it. Now, one idea that you might have is to say, well, maybe this matrix doesn't actually have n squared degrees of freedom. Maybe it's actually a lot simpler. Maybe we can replace it with a low rank approximation, which has, if it has a rank R, has about Rn degrees of freedom instead of n squared. And one type of factorization, which is very useful and very common in these applications, is called a Nystrom approximation. Nystrom approximations are interesting because they're based on identifying a set of salient columns from the matrix, which capture, which are like landmarks or data points that are most important. So if S is a list of column indices, which represent the data points you believe are the most important ones, then you can make an approximation by taking those columns listed in S and the rows listed in S. These are transposes of each other because this is a symmetric matrix, and then sticking in the middle the pseudo inverse of the principal submatrix whose rows and columns are indexed by the data points you picked out. So this matrix tells you how those data points are more or less similar or dissimilar to each other, and its pseudo inverse is a linkage between the columns indexed by your important data points in the rows. Okay. So this is obviously, if you have K indices, a rank K approximation. And as it happens, it's extremely natural. So any questions on the definition before I talk about the properties? Okay, so we're going to try and pick K important data points, and we're going to use the associated columns of the kernel matrix to approximate the kernel matrix well. Okay, so the Nystrom approximation has a number of remarkable features. So the range of the approximation is obviously the span of the columns of the kernel matrix that are indexed by the K data points we picked out. This is obviously positive semi-definite because this is a positive semi-definite matrix, and therefore its pseudo inverse is also positive. And by conjugation, it remains positive. The residual is positive, so if you subtract the approximation from A, that is also a symmetric matrix with non-negative eigenvalues. That's less obvious. It's a nice exercise to try and see why that's true. And among all matrices that have these three properties, this approximation is the smallest residual. And so it has a variational property that makes it exceedingly natural. And that's why this is somehow the best way to approximate the matrix if you have a set of columns that you think are important to you. Okay. Any questions on the properties?
You said the variational formulation. It's a minimization.
Yeah, it's a minimization actually with respect to the semi-definite order, which is kind of nuts because this is like a weird poset, but nevertheless, the problem has a solution. Yeah. So it turns out that this is optimal in an extremely strong sense. All right, great. So to recap, we've got a positive semi-definite matrix, which in our application will be a kernel matrix. We'd like to approximate it by a low rank matrix based on a specific subset of columns, and the Nystrom approximation is a natural way to achieve that goal. Okay. Now, how do we calculate a Nystrom approximation? So one of the beautiful things about this construction is it has a very tight connection with a classic linear algebra algorithm that you know called the Cholesky decomposition. And in fact, Nystrom approximations arise from partial Cholesky decompositions. So here's how this works. The Cholesky decomposition starts out with an initial residual equal to the matrix you're trying to approximate, and an initial approximation equal to 0 because you haven't done anything yet. Okay? So we start out with a 0 approximation, and therefore the amount of matrix we still need to approximate is the whole matrix. Okay. At each step of the algorithm, we pick a new column, a new data point that we think is important, and we add the column of the residual matrix indexed by that column times its transpose. This is a rank 1 matrix indexed by the column we picked from the residual, normalized by a diagonal entry of the residual. So we add this rank 1 matrix to the approximation, and we remove it from the residual because we don't need to approximate that part anymore. Okay, so at each step, we have a residual, we pick a column that we like, we remove a rank 1 matrix from the residual, we add it to the approximation, and we repeat. Okay, so it's adaptive in the sense that the residual is changing at every step, and we need to extract columns from the residual, not from the initial matrix. But at each step, we can repeat this procedure with whatever column indices we choose. And there is a proposition, which again is a nice exercise to show that the approximation after k steps of this partial Cholesky procedure is actually the Nystrom approximation defined by the k column indices that we've chosen. One of the amazing features about this is it doesn't matter the order in which we choose these events, these importing columns. You'll always get this same approximation regardless of the order you do it in. Okay. Now, if you stare at this algorithm for a little while, you can see that we can implement it with only kn entry evaluations because we only look at the k columns that participate in the approximation. We don't actually need to look at any other part of the matrix aside from the k columns. And the amount of arithmetic required to do this is order k squared n. Okay, so we can produce the Nystrom approximation based on k columns using relatively few entry evaluations. And k is a lot smaller than the dimension of the matrix, and using k squared n arithmetic, which again is a lot smaller than n cubed. Okay. So any question on the Cholesky decomposition and how it connects to the Nystrom approximation?
So the proposition means A hat k equals to the one that you mentioned.
That's right.
Use
So
their own data, right? Like use A with the index S.
yeah.
Okay.
So this approximation here on the right, the Nystrom approximation based on the set S equal to S1 up to SK is exactly the same as the eighth approximation produced by the partial Cholesky procedure, selecting indices S1, S2, S3 up to SK. So they're exactly the same thing. Yeah, it's kind of surprising.
Yeah.
Because somehow it's computing this pseudo inverse for you automatically.
Is this also true is if we like choose the SI not according to the method that you mentioned, like the
Yeah, so it actually doesn't matter how you pick the SI, it's always true. Yeah,
That's good.
and that's actually the next question. How do you pick the SI? So how do you decide which columns are important? Okay, so let me give you an example of how this works, and then we'll come back to that question about how we decide which columns are important. So here's the kernel matrix I showed you before for the clustered data points. And I would like to produce a low rank approximation. I believe that I can do that because somehow there's not a lot happening here in this matrix. It reflects the fact that there are two clusters. So why don't I pick the third column first, which corresponds to this data point, and see what happens if I eliminate that. Okay, so here's the first approximation. It comes from me taking the diagonal entry, pseudo inverse, and multiplying by the outer product of those diagonal, the outer product of those, the column and row. So here is that representation. And then once I subtract off this approximation, it leaves me this residual. And you can see that that one data point has explained the other two pretty well. And the block here is pretty small now. And the reason is because having one exemplar from the cluster already does a good job explaining the other stuff that's similar to it. We haven't done much to the blue cluster, though. You can see these entries are still pretty big. So let's say that I pick this fourth column next, which I think corresponds to this blue data point here in the middle. So when we do that, we now have a rank 2 approximation, which is based on these two columns and the reciprocal of the diagonal entry and the associated column, the second column here was drawn from the residual A1.
So they have a print there, so fill it with 0.
Yeah, these entries are 0, these entries are 0, so the spaces are zeros. Okay, so now you can see that we picked this blue guy. It explains pretty well the stuff in the second cluster. This guy explains pretty well the stuff in the first cluster. So now there's not much less in either of the clusters or in the off diagonal stuff. And so we basically approximated the matrix pretty well, just using those two columns. So you can see that in this setting, because we use this kernel matrix that describes locality, similarity of points that are close to each other, picking out an exemplar from each cluster did a good job. And it gave us a good approximation of that kernel matrix that describes the similarities among all the data points. Okay.
So
Any
sorry,
questions
maybe
about this?
Quick one. So the matrix in the middle is always going to be diagonal?
In this algorithm, yes, because the second column reflects what we did in the first step. In the Nystrom approximation, it's not diagonal because it's based on the original columns from A and not from the modified columns that arise from the residuals in the partial Cholesky algorithm.
Like the Cholesky process, just like have a approximation for the pseudo inverse for the dense matrix.
Yeah, that's what's happening. The Cholesky approximation is somehow implicitly computing a pseudo inverse for you. That's pretty cool.
Yeah.
Yeah, they don't teach it this way usually in linear algebra classes, but this is what's going on. All right, good. So now coming back to the question. So if we want to approximate a matrix, how many columns do we need? And then the next question is, how do we pick them? So it turns out that there is an efficient approximation, efficient meaning that it doesn't use that many columns, provided that the eigenvalues of the matrix decay quickly. So there's a result due to Goswami and Senop from 2012, which says that if you would like to approximate your matrix, your PSD matrix A, almost as well as the best rank R approximation. Remember, this is a positive matrix, so the trace is actually a norm. It's a measure of how much is left. And you want to do almost as well as the best rank R approximation. You can achieve that with a rank K approximation when K is a bit bigger than R. How much bigger? R divided by epsilon, the slop factor, plus R minus 1. Okay. So think about epsilon here as being 1. When the eigenvalues decay fast, this error is going to be pretty small, and you can get within twice the optimal error using 2R minus 1 columns. Okay, so this is an existence result. It turns out, sorry, let me actually make sure that it's clear what the claim is of this theorem. Something I can clarify here.
Yeah, I'm just trying to confuse, so the K is bigger than the R, the K is constructed through your Nystrom method, and the R truncated eigendecomposition is just the projection onto the first R eigen.
Yes, exactly.
So that would be as good
That's
as
the best you can do.
R.
Yeah.
But if you do this, and the vectors are chosen how?
Well, I'm about to tell you that.
Okay.
Yeah,
Okay.
there's an existence theorem.
And the first R eigen vectors, then you
Yeah.
got lucky.
Yes, exactly. Well, that only works if somehow the eigenvectors are columns are eigenvectors.
Yeah.
Something like that. Okay. So where does this come from? This is an existence result. It comes from the fact that if you sample columns according to a determinantal point process, then on average you get this found. And by the probabilistic method, therefore, there exists some collection of columns that has this property. So it turns out that this is not really a practical algorithm. And so this sort of tells you what you should hope for, how many columns you need to approximate the matrix almost as well as possible, according to this trace norm metric. But there's still the question about how you build a practical algorithm that identifies those K columns. So we don't know that yet. Because I'm asserting that these determinantal point processes are not really something you can really implement in large scale settings. Okay.
And quick question. When you say there exists a K column approximation, are you referring to a specific class of algorithms, or this can be?
No, this is an existence theorem about positive semi-definite matrices and approximations using column Nystrom approximations. Yeah. Good. So how do we choose the columns? So remember, in the Cholesky decomposition, at each step, we are picking some column out of the residual. This is called a pivot in the context of the Cholesky algorithm. And so we really have this question about how do we pick pivots at each step? Because we saw that in the Nystrom approximation, the choice of the pivots tells you what the approximation is, and it doesn't matter in what order we pick the pivots. But when you implement the Nystrom approximation using the partial Cholesky algorithm, you need to pick the pivots in some order, and then the question is how we do that. So the idea that you should have in mind is that for a positive semi-definite matrix, large diagonal entries are important because of Hadamard's inequality, which says that the off-diagonal entries squared are bounded by the product of the associated diagonal entries. So if you pick out some off-diagonal entry you're interested in, it's bounded by the product of the square of that off-diagonal entry is bounded by the product of the off-diagonals. And this is just a consequence of the fact that the determinant of that little 2x2 matrix is positive. Okay, so what that tells you is that if the diagonal entries are small, the off-diagonal entry has to be small too. And so you can ignore it. So the only off-diagonal entries that can be big are the ones with big diagonal entries. So it's natural to go looking for big diagonal entries. Okay, so the idea that you might have then is to sample the pivot in proportion to the diagonal of the current residual. So at each step, you've got a residual matrix. It's positive semi-definite. So the diagonal is non-negative. So if you normalize by the sum of the diagonal, you get a probability distribution. Or more generally, if you look at the p powers of that diagonal, you can normalize by the LP norm and get a probability distribution. So there are three things you could try to do. There's the case p equals infinity, which is like sampling the biggest diagonal entry every time. Okay, so that's really taking as seriously as possible the idea that you care about the biggest diagonal entry. It's called the greedy or the complete pivoting method. Another thing you could do is say, I don't care how big the diagonal entries are, I'm just going to sample one at random. That's the case p equals 0, where you just treat all of them as being co-equal. So p equals 0, you get a uniform distribution, you just sample a random entry at every step. So that doesn't really satisfy the desideratum that we should care about the large entries. And we're suggesting you do something else, which is to sample in proportion to the diagonal entries divided by the trace. Okay. So this is actually a probability distribution. And it's associated with putting the power 1 here. Okay. So at each step, we think about the diagonal as we're finding a probability distribution, and we sample from it. And that's how we pick the next entry. So this allows us to exploit the fact that large diagonal entries are pointing toward places where the off-diagonal entries might be big. But it allows us to explore some of the smaller entries as well, just in case there's something hiding underneath them that you care about. So it's a balance between exploration and exploitation. Okay, so these two are the items 1 and 2 are the things that people have been doing for 20 years. Strangely, item 3 is more or less new. And even though it's exceedingly natural. Okay, so what we're suggesting here is that you should implement the partial Cholesky algorithm, and in each step you should pick a new pivot at random in proportion to the entries of the current residual, the diagonal entries of the current residual. Okay. Any questions about what we're suggesting here?
So greedy method where you can choose less index than the random methods.
Well, you'll see. I'll show you. So these are all Gibbs distributions with different temperatures, if you like to think about it that way. Okay, ready? All right, let's go. So here are a couple simple illustrations to give you an idea about what can happen. So here are two data sets. The first one, the smile, has 10 to the 4 points, -2, and we're using the same Gaussian kernel that we showed you before. The eigenvalues drop off pretty fast, so you expect to be able to approximate this efficiently with a relatively low rank matrix. The second data set is called outliers. It's a core of points, like an atomic nucleus with a whole bunch of like dots floating around at some remove. You can think about like electrons. This has this crazy step spectrum. So that you expect this might be a little harder to approximate well. Okay. So what happens if you apply these different algorithms I've told you about to approximate these two matrices? So there are two failure modes that the algorithms can have. So on this chart, we have the number of columns we pick on the horizontal axis and the relative trace norm error on the vertical axis. Okay, so how well have we approximated A with a rank K matrix whose columns are chosen according to each of these schemes? So you see that most of the methods produce similar errors, but two of them, uniform sampling and something called ridge leverage score sampling, miss the eyes completely because they just can't see that these are important data points because they're not sticking out enough. Well, the uniform distribution just doesn't notice, right? Whereas this random pivot selection finds the eyes as salient data points, as do these other methodologies. Okay, so one thing you could happen is you could have data points which are important to you, but are not that visible. And so you need a method that can exploit what you've learned about the matrix if you want to find those important data points. Okay, so you want to find the eyes, you need to exploit. Now, the other thing that can happen is with this outlier data point, a data set, you see that most of the methods do equally well in the trace norm error, but the greedy is a disaster. Why is that? It's because the outliers are sticking out and the greedy method just keeps picking them one after the next and failing to find the nucleus. Okay. Whereas the random pivot selection occasionally picks an outlier, but usually it finds stuff in the nucleus because the outliers aren't sticking out enough that they dominate the probability. But the greedy method always picks them because it's so myopic. It can't explore. Okay, so those are the two failure modes you might see among these algorithms. And what's interesting about the random pivot selection is it avoids both failure modes. And as I told you before, uniform and greedy were sort of the go-to methods before. And you can see that both of them flame out for particular data sets. Okay, good. So a few comments on computational cost. The three methods I talked to you about in detail, uniform sampling, greedy, and randomly pivoted Cholesky, don't need to look at very many entries of the kernel matrix, which is great. Okay, so they're pretty efficient. You can see that they're all similar. Determinable point process sampling, the thing behind that existence theorem, requires hundreds or thousands more entry evaluations, and so it just flames out for big problems. You just can't use it. Okay, and so even though in principle it's optimal, it's not practical, and so sometimes the best is the enemy of the good. All right, so now I'd like to tell you a bit more about a more substantive application of these methods. These are just toy examples. I mean, who really cares about what happens for smiley faces? So let me tell you about an application of these kinds of low-rank approximation algorithms for a kernel spectral clustering problem that arises in computational chemistry. And you'll see that somehow this balance between exploration and exploitation of the data points makes a significant difference for the chemistry application. So here's how kernel spectral clustering works. Remember in the first place, I showed you that using a Gaussian kernel can help localize points in clusters. So there are other kinds of kernels that can also achieve that goal. And the idea of kernel spectral clustering is that you are going to compute dominant eigenvectors of a kernel matrix normalized by a diagonal matrix of row sums which makes it into the transition matrix of a Markov chain. So you can think about this matrix D inverse K as describing the transitions of a random walk on moving from one data point to similar data points. Okay. And the idea is that the dominant eigenvectors of this matrix somehow identify features in the data because they tell you about what points are most accessible to each other. All right. And so then the idea behind kernel spectral clustering is that you represent each data point in a basis determined by the leading eigenvectors of the normalized kernel matrix, and then you cluster these featurized points to get clusters. This probably won't make any sense if you haven't seen it before, so I'm not going to dwell on the details. The key point is that you need to perform a linear algebraic computation involving the kernel matrix, and that gives you features that help you identify clusters in a large data set where the clusters are determined by the similarity measure underlying the kernel. Okay, good. So the classical approach to doing this would be to make the kernel matrix, compute all its eigenvectors, and wait until next year. And instead, what you can do is you can approximate the kernel matrix with a low rank matrix, approximate the diagonal matrix of row sums using that approximation, and then compute the eigenvectors of the approximated D inverse K matrix. Okay, so the idea is that if there's not a lot going on in this matrix, a low rank approximation serves as a proxy for the matrix, and therefore you can approximate and then apply the kernel spectral clustering procedure to the approximation, and that is massively more efficient. K squared n versus n cubed, where you should think about K as being hundreds and n as being tens of thousands. Okay, so one application of these ideas in computational chemistry is something called finding metastable conformations of a molecule. So a lot of proteins can move around, but they have preferred configurations. And the function of the protein is determined by the configurations that it prefers. And so then the question is, given data about the positions of the atoms in a biomolecule, can you use that data to identify the most stable conformations of that molecule? So the input are the positions of the atoms in some molecule called alanine dipeptide, and as it happens, the metastable states are described well by two angles, two dihedral angles inside the protein, but you don't know that because it's not what's given to you as data. Okay. And instead, you just see where the atoms are. You don't know what the dihedral angles are between the two arms of this molecule. And so if you use this data on the 250,000 simulated sequences of atomic positions, and you try and use the direct method, you can't do it for all the data because there's too much of it. 250,000 cubed is not great. And so the chemists who proposed this application subsampled the data because they couldn't handle all of it, and then used a workstation for more than a day to produce the result. So the algorithm I described to you, this randomly pivoted Cholesky method, which picks out some number of important instances, simulation sequences, and solve the spectral clustering problem in 10 seconds for 250,000 data points. So you're seeing some improvement. And so with 150 columns, so rank 150 approximation, you can produce this clustering, which is I've shown you in the dihedral angle space, which really makes it clear what's going on. And you see that there are 1, 2, 3, 4 clusters. And remember, because these are angles, this is a torus, and you glue the top and bottom and the left and the right together. Okay. So in short, this is a benchmark application in computational chemistry. And by using a little bit of computational mathematics and a new algorithm, we're able to speed this up a lot. And still produce a solution which is essentially optimal. And so what we've indicated here are the data points that the algorithm has picked out as being the most important ones.
So how do you start your algorithm? How do you finally decide that like 150 enough?
That's a good question. I actually don't know what my postdoc did to decide when to stop. I mean, it's like one of these things where you can look at a sequence of solutions and then see when it stabilizes. And at that point, you're not getting any benefit from continuing. So that's probably the approach that he's taken. So what I can show you here is the sequence of results that you get as you vary the number of columns you pick out. And on the vertical axis is the clustering error on a log scale. I think when he says clustering error, what he means is misclassification. You put points in the wrong place as compared with the reference solution. And what you see is that the random choice of pivots makes steady progress. And then at this point, that's already enough to match a reference solution that's computed with much higher precision. But you still reduce the clustering error more if you keep going. So in this case, we actually knew what the answer was. So we just compared with that. You see all the other algorithms are unsuccessful. The greedy algorithm seems like it's eventually starting to catch up, but at first it's, I mean, just going sideways. It's like not even making any progress. And so you see that somehow this balance of exploring and exploiting when you're picking out data points to produce this approximation really, really helps. You know, here at 150, the difference between this curve and the other curves is again a factor of 10 to 15. So there's a huge improvement in the cluster performance by using this method. Okay. All right, any questions about this algorithm, how we applied it in this application? I think the benefits are pretty clear from the numbers and from the plots. Yeah.
Sort of a strange question. Did the data come from Mark Tuckerman's group?
I don't know.
But I've seen us, he gave a talk about this 10 years ago on
Yeah. It's a benchmark example.
This is a standard benchmark.
This so I don't know where the simulation data came from. These are simulated time series for these molecules. But this was an editor's choice paper in one of the computational chemistry journals about 3 or 4 years ago. So it's definitely not that old. You know, this is kind of old hat in the computational chemistry world. They're not so interested in linear peptide, but at the same time, it is one of the standard examples is a real scientific problem, which is indicative of the kinds of things that they would like to accomplish.
So the approach I've seen before was sort of an important sampling approach with umbrella sampling where you fill in things, and that doesn't quite fit into any of these.
No.
If I understand.
No, my postdoc could probably answer this question better because he is an MCMC expert, but yeah. All right, so this is a computational math talk. So after showing you some of the failure modes for the different algorithms, you can see that like it's just getting confused about what points belong in what cluster. I'd like to say a little bit about the theory before we wrap up. Okay, great. So my feeling is that algorithms are designed to solve problems, and that it's great if you have a theoretical foundation and that the method is well justified. But in the end, I do view this as somehow secondary to the actual practical value of the methodology. So nevertheless, I do think it's important to understand how algorithms work, why they work, what you can hope for. And so we did a theoretical comparison of randomly pivoted Cholesky as compared with some of the other methods for low rank approximation of positive semi-definite matrices. So as I told you before, if you want to achieve something, an approximation that's comparable with best rank R approximation, by using a rank K approximation, and you're allowed a slop factor of epsilon, the best available bounds for the other methods are here in this table. So if you use a determinantal point process, you get this bound, which is optimal. You can't improve on this. And what we will argue is that the randomly pivoted Cholesky algorithm gets the same leading factor plus r times a logarithmic factor that depends on the slop factor epsilon and the dynamic range eta, which is the quality of the best rank R approximation divided by the trace of the matrix. Okay. Now, from a practical point of view, eta can't be bigger than 10 to the 16th in double precision. So you should be thinking about this logarithm as smaller than 37. Okay, so it's a relatively small number. And so even though 37 is bigger than 1, you don't expect to see a huge difference between these two algorithms. And in fact, we saw in practice that they perform exactly the same, or sometimes the random pivot choice is a bit better than this method-based determinant point processes. Okay, so
usually very small, so that's why we consider leading term will be sort of sufficient, right?
well, it depends on how big epsilon is. I think about epsilon as being 1. So the second term might actually dominate. But I mean, practically speaking, we don't see a difference between these algorithms, and we wanted to understand why. The analysis we did, which I'll tell you a little bit about, does have a dependency on the dynamic range of the problem and another dependency on epsilon, but that is logarithmic rather than polynomial. So the epsilon here is somehow not important. The important part here is the eta within range. Okay, good. So as I indicated, we were able to prove a theorem about this, which tells us that the randomly pivoted Cholesky algorithm generates a nice term approximation using k columns, whose expected error is comparable with the best rank R approximation, provided that the number k of columns is a bit bigger than the rank of the target. Okay, so say a few words about how this works. So the first idea is that we're going to look at the expected residual after one step of this algorithm. So after taking one step, we remove this rank 1 matrix, and we'd like to know the expectation of the new residual conditioned on the old residual. Okay. And to do that, we simply multiply by the sampling probabilities and add up. Now, the diagonal entry cancels, and we see this beautiful compact form for the expected residual. It's the current matrix minus its square divided by the trace. Okay, so this is a very easy calculation. It just tells us what you anticipate after one step of this partial Cholesky procedure, selecting pivots at random. Surprisingly, this is a function that is both monotone and concave with respect to the semi-definite order. So it has some nice algebraic geometric properties. And as a consequence of that, if you run k steps of this algorithm, on average, it's no worse than the trace of this expected residual map composed with itself k times and applied to the initial matrix. I don't want to go through the details. But it's basically just Jensen's inequality and monotonicity over and over again. Okay? So the point is that the expected error in the kth residual is bounded by the trace of k applications of that map applied to the original matrix. Maybe not so surprising. Okay, now at this point, there's an interesting sequence of steps. So because the right-hand side here only depends on the eigenvalues of A, because phi is a polynomial function or a rational function of A, it only depends on eigenvalue. So we might as well pretend A is a diagonal matrix, because This function can't tell the difference depending on the eigenvectors. So once you understand that we can take A to be diagonal, the question is, what's the worst case? Well, if we fixed the choice of R, the target rank, the worst thing you can do is make the first R entries of the matrix the same and the remaining entries the same. And that's true by concavity. Okay, so this is the part you're approximating, this is the part you're not approximating. And so the spectrum of the worst case matrix should have this step form. Okay, now, by definition, if you apply the expected residual map K times, it preserves the form of this matrix, but the A's and the B's change because it's moving the errors around. And you can see that there is an explicit upper bound for the error in terms of these numbers. And these numbers satisfy this complicated difference equation. Okay, I don't like difference equations because they're hard to solve. So instead, we replace this difference equation by an ODE. And because the right-hand side here is negative and decreasing, the ODE bounds the solution to the difference equation. So we solve the ODE by separation of variables. We discover that if we run the ODE for long enough, its value is small in comparison with the initial error. And we have a bound here for how long we need to do that. And that translates directly back into the number of steps of the Cholesky algorithm we need to perform. Okay, so in short, this analysis tells us that this randomly pivoted Cholesky procedure does produce low rank approximations that are competitive with the best low rank approximation, and it gives us a bound how long we need to run the algorithm. It's a little bit worse than you get from determinable point process sampling, which is the optimal method, but nevertheless, it puts them in the same ballpark and it helps us understand why this method might be competitive in practice. And what we've actually seen is that we can apply this algorithm to examples that you can't address with other methods. And in fact, its performance is best in class across a range of synthetic and real data problems. Okay, and so the reason I think this is interesting is one of the simplest examples of how randomness can help us solve linear algebra problems efficiently, even though there's no obvious reason that you should be using randomness in selecting the pivots for a low rank approximation of the Cholesky method. And yet, this very natural, straightforward strategy gives you an efficient algorithm that is easy to implement. It looks at very few entries of the matrix. It works extremely well in practice, as well or better than the alternatives. And we were even able to establish a guarantee that confirms what we've seen from the empirical performance. All right, so we've finished the hour. I want to thank you all for your attention. I will hang out here in Michigan State and answer questions for a little while or chat with y'all. And for those of you who are in radio land, thank you for joining.